we've talked a lot about trees. We've talked a lot about the circumference of trees and trying to analyze the data based on those things and trying to get some understanding as far as how to work on graphs, how to calculate standard deviations and z-scores and all that kind of stuff. But we've only been using one set of data. We've been using one measurement. We've simply been using the circumference of trees and trying to analyze a population with one particular variable. What happens if we're trying to see, is there a relationship between two different variables? That is called the analysis of bivariate data. So we're going to call this bivariate, it's an I, that's a T, bivariate data, okay? That's simply nerd for we have an X coordinate and we have a Y coordinate. We have an X and a Y. You can't really see the Y, the string's in the way, but it's right there. There it is, I promise. All right, so we have an X and a Y. You have X and Y numbers, and we're going to plot them on a graph, and we're going to try to see what's going on. So I thought it'd be very appropriate, since we are in isolation from each other. We've been commanded by our authorities that we are to stay within, not get within 6 feet of everyone, not cluster in groups of more than 10 at a time unless you're family. I mean, all that kind of crazy stuff, right? Question is that really necessary? Is there really an effect that this could have? Well, we can analyze this. So we're going to look at data today, and we're going to look at, I pulled these numbers from the New York Times website, where I pulled the number of cases in particular counties around the country, just random counties where there was a lot of different cases, and we're gonna create a graph. It's just simple 6 data points. We're gonna look at these things and try to analyze these numbers and try to figure out what exactly is going on, and is there a reason? Is it justified, this whole isolation, quarantine, stay away from everyone, don't go near people? Is it really justified? Well, let's look at the data and let's find out. We're going to look at real-time data. Here we go. So what I've done is I've graphed out a graph here. We're going to look at about six different counties, each of these counties containing a major city. We're going to look at 6 different counties around the country, and we're going to look at their population in millions. Now, this is going to go on the x-axis. This is my x-axis out here. The x-axis across the bottom is the dependent variable. The x-axis is where we put that thing that is not going to change, okay? So notice I put population of these cities there on the x-axis. The reason I did that is because the population, in a sense, is independent of whether or not there's an illness or not. If a city has 1 million people, it's going to have 1 million people whether the people are sick or whether the people are well. Now, you could argue that once the people get sick, if they die, the population goes down. But it's not going to go down to an extreme amount where it's really going to affect greatly the population. So the population is independent. That was there before the illness came. You with me? So then on the y-axis over here, this is my y variable. This is called the dependent variable. This is where I'm going to put the COVID-19 cases, and this is going to be in the thousands. This is going to be in the thousands. Okay, so as I'm plotting out these COVID-19 cases, this is the data that I got from the New York Times. Population for these different counties. I simply went online and typed in the population of whatever county I was looking at, and you can get all that data on the website or on the internet. So that's what I've done, and I'm going to plot out this data, and let's see what kind of relationships that might happen. All right. So the first one is Cook County, Illinois. This is where Chicago is. Chicago has 5.2 million people and almost 11,500 cases. So 5.2 million would be here, and 11.5 cases would be right about there. So I'm going to put my data point right there. And there's my Cook County, okay? Next one is Orleans Parish down in Louisiana. This is where New Orleans is. Orleans Parish, they only have just under 400,000 people, but they have a death rate. The number of cases there, actually not death rate, forgive me, the number of cases there is about 5,200. It's over 5,200. So at a population of about 0.4, but yet they have 5,200 cases, that would put that data point right there. Next one is good old-fashioned Jeffco, Jefferson County, Alabama. Roll Tide. All right, so Jefferson County, Alabama has population just over 500,000 at 600,000+. So that would put my population right in here, but we only have 523 cases at the time doing this. So that would be less than 1,000. So that would put my data point right there. Miami-Dade, Florida. That is 2.7 million and almost 6,000 cases. So 2.7 million and almost 6,000 cases. That would put my data point right about there. King County, Washington, I believe that's where Seattle is, has 2.2 million and 3,888 cases. So almost 4,000 cases. So let's see here. King County has 2.2 million. So that would be right in here. My population, 2.2 million. And I said there was almost 4,000 cases. So that would put my data point right there. And then we have the last one is Fulton County, Georgia. I believe that is where Atlanta is. And that is a population of 1 million. And there is just over, not quite 1,500 cases. So 1 million, and I would put my data point right about there. Now you can already see something very, very interesting, and that is that these data points right here seem to make a straight line. But we've got that little goofy one sitting out there on the side. That is an outlier according to the data. Now we only have 6 data points, and there are tens of thousands of cities and communities and counties in this country. There's lots of them. So we're only taking a small sample, but let's see if there's any kind of relationship. So in doing this, what I've created here is called a scatter plot, where I've simply taken my dependent or my independent variable population, my dependent variable, the cases of COVID-19, and I've simply compared the two. What I'm asking is there a relationship to population density and the number of COVID-19 cases? Can I demonstrate that there is a relationship between them? So what I'm going to do is I have to calculate this out. And if there is a relationship, by the way, how strong is that relationship? How strong is it? So what I've done is there is a formula that you can use to calculate this. It is called the linear, I have to remember it, the linear correlation coefficient formula. That's a mouthful. Linear correlation coefficient. And what this formula does is this formula tells me, when I fill out all the data, it tells me whether or not there is a strong relationship between my two sides, right? So let me show you what that formula is, by the way. The formula is really, really ugly. That's what it looks like. So we have n times the sum of x and y minus the sum of x times the sum of y, all over and divided by the square root of n times the sum of x squared minus the sum of x squared times the square root of n times the sum of y squared minus the sum of y squared. And that gives us what is known as an R value. That's what all these symbols mean. This is the mathematical symbol for a really, really ugly equation. And there it is. Okay, good. So that's the equation that I'm running. You can find it in textbooks. You can find it online. But what it's going to do is, in plugging in all of that data, what it's going to do is it's going to tell me, it's going to give me what is known as the R value. The R value is a number that exists between -1 and 1. Okay, -1 and 1. A 1 for an R value means that there is a positive, strong relationship. That means that for every as we go up in population, we are going to go up in cases guaranteed. It is a one-to-one relationship. You're shooting straight up. It is a positive correlation. A negative one is a negative correlation. That would say that the more population there is, the fewer cases we have. All right, so we would go in the exact opposite direction. A positive correlation, a 1 would have a graph that slopes up to the right. A negative 1 would have a graph that slopes down to the right. Okay, so that's how we read those. A 0, if I get an R value of 0, what that says is there's no correlation. There's no relationship at all between my X and my Y variables. None. Okay, so usually you end up with a number somewhere in between 0 and 1 or 0 and negative 1. The closer you are to 0, the less chance there is, the less confidence you can have that your data are related, that there's an effect going on here. The closer you are to 1 or negative 1, the stronger you can have confidence in the fact that there might indeed be something that's going on. Well, I've taken the time to run all these numbers. It took me about a half an hour because I did them by hand. You can go on to Microsoft Excel or other data processing programs, and you can simply plug in your numbers and highlight everything and do a linear correlation coefficient. You click on the button and it does it. It's really nice. It doesn't take a half an hour. It takes however long it takes you to type in the data. It's very exciting. Okay, but I did it by hand because I wanted to try to understand it. And what my hand gave me was an R value very, very close to 1. What does that mean? That means that I have strong confidence, very strong confidence, that the greater the population density, the greater the number of cases we're going to get. And you can see that in this graph. The best fit, that line of best fit goes right through that area. That was almost a straight line of those things, which told me, even looking at those numbers, that that was indeed something really, really, really powerful was going on. I ran the numbers, and sure enough, my R value was very close to 1. Great confidence. What does that mean? That means that this whole social distancing thing, as uncomfortable and miserable as it is actually a really good thing to do. It's a very, very good thing to do, as hard as it is. That's what this data tells us. Now, let's ask this question. What the heck is going on right there? Remember, that data point right there was from Orleans Parish, which is where New Orleans is. We have this low population and this exceedingly high number of cases, way disproportionate to what should be on our graph. So why is that data point sitting way up there by itself? That is called an outlier. Whoops. And an outliers tell us one of a couple of things. Either something really weird is going on, there was something wrong with your equipment when you were doing the measuring. It could tell you that you've done your math wrong. It could tell you all kinds, it could be human error in there, or it could tell you that there's something weird that happened in that area that caused that number to be different from everywhere else and to not fit in. Well, New Orleans said yes during the month of January, February. They said yes to celebrating Mardi Gras. And people came in from all over the world, and they spent the whole week all doing Mardi Gras, hanging out, drinking, partying, large groups of people all intermingling. They said yes to that. That's the explanation for the outlier. That's why that happens. Small population, but because of anti-social distancing, their cases spiked. This is where we are with social distancing. This is where we would be if we did not have social distancing. So, again, as uncomfortable as it is, social distancing is a good thing. Okay? It really does have a positive effect on keeping these cases as low as we possibly can. So, this is how you get an R value by calculating the linear correlation coefficient. That's what R is. If you're close to 1, you have strong confidence that there is a relationship, a positive relationship between your X and your Y. Positive meaning that as X increases in number, your Y is going to increase in number. All right. If it's close to a -1, you can have great confidence that there's a negative relationship, that as X increases in value, Y will decrease in value. If it's right at 0, that means there's really no relationship. You have zero confidence at all that these two numbers have any kind of relationship at all together. This is a simple way of analyzing what's called bivariate data, where you have simple X and Y looking for the possibility of a cause and effect. Does this produce a cause and effect? Not necessarily. Remember, correlation does not mean cause and effect. There is a correlation between roosters crowing and the sun coming up. But I promise you, if we kill all the roosters, the sun will still come up. And if we stop the sun from coming up, odds are the roosters will still crow. Especially mine. I have stupid roosters. They crow all the time. It could be 4 o'clock in the morning and they're still crowing. It could be 3 o'clock in the afternoon and they're still crowing. They're kind of annoying that way. But I digress.